Welcome to the pre-calculus video for skill number 15. I can find the domain and range of a function algebraically and graphically. And featured below is a compass rose, and the trivia question for the video is, what athletic team uses a compass rose as part of their team logo? If you're looking for examples beyond this video, feel free to check out the AB Calculus video 105 for more examples of domain and range. And on with the lesson. We'll begin our notes on page 15a. When we're given a function, such as y equals f of x, the domain is considered the set of all input values. And our domain can be restricted by the function, and this skill is going to be talking about how to find what the restriction on the domain is. The range is the set of all output values. So, for example, if we had the equation y equals x squared, we can put whatever we want in for x, so our domain is all real numbers. However, our range, whatever we put in here is going to spit out a non-negative number. So our range is y is greater than or equal to 0. So before we get into finding what our domain and range is too much, I wanted to take a look at two examples of mapping diagrams that demonstrate what a function is. So for a rule to be considered a function, each input generates only one output. So here x1 gives us one output, x2 gives us one output, and x3 gives us one output. So this is considered a function. The mapping diagram on the right, it shows that x1 can actually provide two different outputs. And because that is the case, this is not a function. The meat of this skill is in finding what the domain and range is, either algebraically or graphically, and for the skill test we'll need to be able to do both. So let's take a look at some tips for finding the domain for a given equation. Generally you can start with all real numbers, and then you want to start eliminating numbers that do not work. For example, we want to eliminate any values which create negative square roots. So if I had the square root of x, then my domain has to be x is greater than or equal to 0. If I had the square root of x minus 1, then the domain is x has to be greater than or equal to 1. Because if we put in any number less than 1, then our value under the root would be negative. The next statement is eliminate any values which make the denominator equal to 0. So since we're not allowed to divide by 0, our domain takes on all x except 0, so x does not equal 0 in that case. Or if I had like 1 over x minus 3, we would get all real numbers except x does not equal positive 3, because that puts a 0 in the denominator. And one last tip would be eliminate any other values not permitted by the operation. For example, the natural log of x, or really any logarithm of x, we cannot take the log of a negative number, so the domain for this is x is greater than 0. Similarly, our trig functions sometimes create restrictions. We're not going to get into those restrictions too much until later on in the year. But for example, tangent x, we could not put pi over 2 in there because tangent of pi over 2 is undefined. But we'll get into that further in the year, so don't stress the trig functions. So example 1 here demonstrates find the domain of the given functions. And I like to sometimes think about these graphically while I'm thinking about the function. For example, x to the third is a cubic function, and we can see the graph looks roughly like that. Our domain is all real numbers because we can plug anything into it. For the square root of x, our domain is only x is greater than 0, greater than or equal to 0. If we wanted to Look at the next one, 1 over x, the graph of that rational expression looks something like that, and we wind up getting x cannot be 0. We have a vertical asymptote there. The absolute value of x we can plug anything into, so we have an unlimited domain of all real numbers. No zeros in the denominator on this next one, so x minus 7, we cannot have x equal to 7 or else that puts a 0 in the denominator. The next one here is actually kind of difficult. We have two restrictions. We either have 2x plus 3 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 3 halves. And then we also have the second restriction where x cannot be 0. And if x can't be 0, our interval notation for those two things combined is from negative 3 halves to 0, don't include 0, and then from 0 all the way to infinity. In our next example, our denominator is not factored, but if we were to factor our denominator, we would have an expression that says 2x over x minus 5 times x plus 3. And you can see how that leads to a domain restriction of x cannot be 5 and x cannot be negative 3. Because if we plugged either one of those values into our equation, we would be dividing by 0. Finally, we have the third root of x, and all odd roots, you can put whatever value you want in to the radicand, so the domain is all real numbers. When it comes to finding the range from functions, it requires just a little bit more analysis. And the tips I offer are visualize the graph and also understand the operation that is happening. So on the next page we'll look at some examples of this. Find the range of the given functions. So the first function is x cubed, which looks roughly like that. And so you can see that the range is all these y values. It exists everywhere from y equals negative infinity to infinity. Whereas if we took a look at our second graph, the square root of x, the only spot that it exists is when y is 0 or greater. And finally, the last one here, x squared, looks like that roughly, and that's another case where you only have y values from 0 and greater. So a few more examples on the next slide. The absolute value of x. If you take the absolute value of anything, it's going to be positive or 0. So that's how we get a range of y is greater than or equal to 0. The next example, we have a parabola that has been shifted up 4 units. So using that understanding of transformations helps us see that the range is from 4 to infinity, or y is greater than or equal to 4. The next absolute value function is just a shift to the right. So with that, our range should not change. Our range is still from 0 to infinity. Going down the list, you can kind of see these are transformations of some of the above ones, and I encourage you to sketch a rough graph to understand why the ranges are as listed. So since I'm suggesting drawing the graph, I suppose it would be important for us to understand how to find domain and range from a graph. So what I suggest is to find the domain from a graph, what you're going to do is you're going to sweep left to right and list all of the x values that exist, or if there's discontinuities or absence of x values. So in this case, as we move from left to right, all of our x values are accounted for, so our domain is all real numbers. And in the second example, what we have is, as we sweep from left to right, x values exist, and then right here we have a hole at x equals 2. So because we have a hole there, we can say x does not equal 2, and then it continues to exist for the rest of the graph. For range, we're going to sweep from the bottom to the top, so what we have is does not exist all the way up until we hit -1, and at that point the graph does start existing, and it continues to exist all the way up, so our range is y is greater than or equal to -1. And finally, on the last graph, we do the same thing for the y values for range of the parabola. We have y values down here, keep going, y values exist all the way up to 3, and at that point they cease existing. So y has to be less than or equal to 3. Thank you for watching the video for skill number 15 and the answer to the trivia question. The Seattle Mariners use a compass rose in their team logo. I would also encourage you to check out the AB Calculus video 105 for some more examples of domain and range, both algebraic and graphic. Thanks for watching.